Hey, double E sauce, Ryan here. What is the most complicated differential equation you can think of? First order, second order, partial differential equation? What if I told you that there's an easy way to solve all of these?
To understand how, we need to go back to the basics. Kirchhoff discovered two fundamental rules that apply to all circuits, the voltage law and the current law. The voltage law states that over a closed loop, all the voltage gains and drops sum to zero. For example, if this battery is 5 volts, we know that the top resistor drops 0.5 volts and the bottom resistor drops 2 volts, then we know that the last resistor must drop 2.5 volts to sum to zero. Pretty simple, right? The current law is even simpler. As you can see, the cars entering an intersection must be exactly equal to the cars leaving an intersection. Cars don't spontaneously appear or disappear, and neither does current. Kirchhoff's current law tells us that the current flowing into a node must equal the current flowing out of a node.
That's all great, Josh, but why do we even have voltage in the first place? Well, that would be because of resistance. How do you calculate resistance, you might ask? Well, that depends on the configuration. Let's go back to the car analogy.
Think of traffic lights as resistance. As you can see, if a car has to pass through multiple traffic lights, it takes longer for it to get to its destination. Resistors add in series. However, if we put stoplights in parallel, more cars can pass through because there are more lanes available for travel. So resistors in parallel drop resistance. In parallel, resistance can be calculated as 1 over the sum of the inverse resistances. Let's do an example. If you have 3 resistors that are in series, with their values being 1 kiloohm, 2 kiloohm, and 3 kiloohm, to get the total resistance, you would just add them all together. So 1 kiloohm plus 2 kiloohm plus 3 kiloohms equals 6 kiloohms. However, if you put the same 3 resistors in parallel, you would calculate the total resistance as 1 over the sum of the inverse resistances. So you would add 1 over 1 kiloohm plus 1 over 2 kiloohms plus 1 over 3 kiloohms and take the inverse of that to get a total resistance of 545 ohms.
So what do you do if there are multiple sources in a circuit? Cry? Drop out of school? Hold on there. All you gotta do is apply the principle known as superposition. If you're removing a current source, you open the circuit to ensure no current is flowing along that branch. However, if you want to remove a voltage source, you short the circuit to make the effective voltage drop 0. Principle of superposition says that you can evaluate the circuit with each source individually and then add them together to get the total response across the entire circuit.
Now remember back when we told you that there's an easy way to solve differential equations? Well, to do that, we have to use the frequency domain. To get to the frequency domain, you have to use this long, complicated convolution integral. But you don't need to know all that. Just look at this Laplace table right here. In fact, you don't even need to know all these. You just need to know the ones for certain components. For example, a resistor's impedance is just its resistance. An inductor's impedance is S times its inductance. And a capacitor's impedance is 1 over S times its capacitance. Pretty easy, right? Let's do an example.
Suppose you had an RLC circuit, with the capacitor being 1 picofarad, the inductor being 0.1 Henry, and the resistor being 1 kiloohm. In order to solve for the transfer function of this circuit, you would simply do nodal analysis at the output node, setting the current into the node equal to the current out of the node. For the impedances, you would use the resistance for the impedance of the resistor, 1 over S times the capacitance for the impedance of the capacitor, and S times the inductance for the impedance of the inductor. When you plug all these in, you can solve for V out over V in. This gives you a transfer function, h of s, of 1 over s squared times 1 times 10 to the negative 13 plus s times 1 times 10 to the negative 9 plus 1.
So what can you do with these transfer functions? Well, if you have an input in the S domain, you can multiply it by the transfer function and get the output in the S domain. And you can use this to create all kinds of circuits that block and pass certain frequencies, but we'll save that for another video. For now, go out and use those S domain equations to make your life 100 times easier. And as always, thanks for watching.